Hi, good morning. This is Srinivas sir. You are watching Untold Botany. Today I would like to discuss quantum requirement and the relation between the oxygen evolution and the synthesis of the glucose. Here, quantum requirement first we should know. What it is the quantum requirement? Quantum requirement is the light quanta that are required for the evolution of one oxygen molecule. Actually, the photosynthetic yielding is measured in terms of oxygen evolution. If 6 molecules of oxygen is evolved, that is equal to 1 glucose molecule. Means to produce 1 glucose molecule, 6 molecules of oxygen should be evolved. So here, to evolve 1 oxygen molecule, how much light quanta is required? The same is considered as quantum requirement. Actually, quantum requirement is equals to 8. 8 light quanta are required to evolve 1 oxygen molecule. How the oxygen molecule is produced? Oxygen molecule is produced from water molecules. So, water molecules, they undergo photolysis, a non-cyclic photophosphorylation, otherwise jet scheme. In a non-cyclic photophosphorylation, when water molecules undergo photolysis, oxygen is evolved. Not only oxygen is evolved, but also NADP is reduced to NADPH plus H plus. We discuss the mechanism. So here, for the evolution of 1 molecule of oxygen through the jet scheme or non-cyclic photophosphorylation, we need 2 water molecules because 2 water molecules undergo photolysis resulting in the formation of a molecule of oxygen. 2H2O, 2O, O2, that is. And simultaneous with the formation of the O2, even the NADP also reduced to NADPH plus H plus. 2 NADPH plus H plus also produced in association with this evolution of the oxygen. Even 2.6 ATPs are also produced. So when one oxygen is evolved, it is coupled with formation of 2.6 ATPs and 2 molecules of NADPH. We discuss the mechanism. So that takes place in one jet scheme or non-cyclic photophosphorylation. Coming to the mechanism of the photolysis, how the photolysis takes place. What it is the photolysis? Who observed the photolysis? Photolysis observed by Robert Hill. That is called Hill reaction. That is why. So here photolysis is nothing but the lysis of the water in the presence of photo. Photo means light. So lysis of the water molecules in the presence of light is said to be photolysis. When water molecule undergoes photolysis, H2O results in the formation of H plus plus OH minus. It undergoes ionization. 2 ions are formed, H plus ions, OH minus ions. Actually, it is represented like that. But actually, what happens? 2 water molecules. To evolve oxygen, we need 2 water molecules. When 2 water molecules undergo photolysis, that results in the formation of 1 molecule of oxygen. 2H2O, 2O, O2 released. 2H2, 2 into 2H2. 2 into H2 means H2, 2H2, 4H. 4H, each H consists of, each hydrogen consists of 1 electron, 1 proton. So 4H consists of 4 protons, 4 electrons and 1 oxygen is evolved. So 2H2O undergoes water photolysis resulting in the formation of a oxygen and even 4 electrons, 4 protons which will be used for the reduction of the NADP into NADPH plus H plus. We discuss the mechanism. And here actually what happens is the true mechanism is this. Net amount of water that undergoes photolysis, 2 water molecules to evolve the 1 oxygen. But the actual mechanism is 4 water molecules undergo photolysis like this. In the ionization, 4 H pluses are resulted. Even the 4 OH minuses also resulted. Now this 4 OH minus, from them electrons are removed. So that results in the formation of 4 electrons and 4 OH. Earlier OH minus ions, now electrons are released, only 4 OH. Now these 4 OH can form 2 H2O plus oxygen. So 4O, 1, see here 2O, 1 O2 and remaining 2 water oxygens are in the water. So 2H2O plus O2. 4 OH can form 2H2O plus O2. Actually 4 water molecules are undergoing photolysis, but Again, 2 water molecules are recovered. Only 2 water molecules only releases electrons and protons, which will be utilized for the reduction of the dirt. This we can multiply with 6 for the formation of a glucose. Totally 24 water molecules undergo photolysis. Of them, again 12 water molecules are recovered, and 24 electrons are produced, and 24 protons are produced, and 12.5 6O2 will be released for the formation of a glucose molecule. Okay, here coming to the reduction mechanism, when 2 water molecules undergo photolysis, that results in the formation of 4 electrons, 4 protons. As I said, 2H2O, 2O, O2 released, 2H2, 4H. Each H consists of 1 electron, 1 proton. 4H consists of 4 electrons, 4 protons. That is, so of these, here NADP plus, which is oxidized state. So it takes 2 electrons, so that NADP plus is reduced to NADP. In the further reduction, 2 electrons, 2 protons are added, so that further it is reduced to NADPH. Remaining 2 protons are added now, so that it results in the formation of NADPH plus H plus. Actually 4 protons, 4 electrons. In the first step, 2 electrons are added, so that reduce it to NADP. In the second step, 2 electrons, 2 protons are added, so that further reduce it to NADPH. In the last step, 2 protons are added, so that results in the formation of 2 NADPH plus H plus. For the evaluation of 1 oxygen, 2 water molecules are photolysed and 2 NADPH are formed. Actually, for the reduction of NADP, who donates the electrons? In the electron transport system, we have seen PS1 donates the electrons. In the PS1, electron deficiency is created, that is fulfilled by PS2. In PS2, electron deficiency is created, so that is compensated by water molecules. So water molecule donating electrons to the reaction center P680. So in other words, we can say that water molecule donating the both electrons, even the protons, for the reduction of NADP. And here, if you see for 1 molecule of oxygen, 8 protons are accumulated in the lumen, because for the 1 molecule of oxygen, means to evolve the 1 molecule of oxygen, 2 water molecules undergo photolysis. So 2 water molecules, when they undergo photolysis, 4 protons are resulted. In the photolysis, electrons also released. So that electrons are transported through the electrons carriers actually. First itself, from the P680, electrons are transported. Later, electron deficiency created. These are transferred to that P680. However, during the transport of that electrons of the PS2 or P680, 4 protons are pumped into the lumen from the stroma. So during the evolution of 1 oxygen, 4 protons are pumped into the lumen from the stroma. However, water also releases 4 protons through the photolysis process. So that for the evolution of 1 oxygen molecule through the non-cyclic photophosphorylation, 8 protons are accumulated in the lumen. Of that 8 protons, 4 protons come from photolysis of the water. Remaining 4 protons come from stroma, because that plastoquinone, which is a hydrogen carrier that releases, that pumps the protons into that lumen. So during the evolution of 1 oxygen molecule through the non-cyclic photophosphorylation, 8 protons are released, or 8 protons are accumulated in the lumen. For 6 molecules of oxygen, how many protons are accumulated? For 1 molecule of oxygen, 8 protons. For 6 molecules of oxygen, through the non-cyclic photophosphorylation, 6 into every time 8. For the evolution of 1 oxygen, 8. For the evolution of 6 oxygens, 6 into 8, 48 protons. 48 protons are accumulated in the lumen during the evolution of 6 molecules of oxygen. So, to accumulate these 48 protons, 12 water molecules should undergo photolysis. So, from the photolysis of water, 50% of the protons. Out of 48, 24 come from photolysis of the water, remaining 24, every time 4, 6 times, come from the stroma. So, together 48 protons are accumulated. We know 1 ATP needs 3 protons, means for the formation of 1 ATP, 3 protons are needed. When 1 ATP needs 3 protons, total we have 48 protons by 3, means 16 ATPs can be formed. When these all the 48 protons, if they go back into the stroma, it results in the formation of 6 ATPs. For 6 molecules of oxygen evolution, means during the evolution of 6 oxygen molecules, 16 ATPs are produced. For the evolution of 1 oxygen molecule, 16 by 6, that equal to 2.6 ATPs. Actually, here the protons which are resulted in the photolysis not only involve in the formation of ATPs through the chemiosmosis. Through the chemiosmosis, they come back. While coming back, they form ATPs. After coming into the stroma, again the same protons are added to the NADP. So that gets reduced to NADPH2. Means the photolysis of water results in the formation of electrons and protons. Both the electrons and protons are finally transferred to NADP, means for the reduction of NADP into NADPH2. Protons, they play dual role. One is formation of ATPs through the chemiosmosis, and even for the reduction of that NADP into NADPH also. Okay, for the formation of one glucose molecule, 6 oxygen molecules are evolved. If 6 oxygen molecules are evolved, that means one glucose is formed. So, for this we need 12 NADPH. Actually, we need 18 ATP, 12 NADPH. But during the evolution of 6 oxygens, only we get 12 NADPH and 16 ATP. Because during the evolution of 1 oxygen, we get 2 NADPH, 2.6 ATP. For the 6 molecules of oxygen, 6 into 2, 12 NADPH, 6 into 2.6. 6 into 2.6 equal to 16 ATP. 6 into 2 NADPH equal to 12 NADPH. Only during the evolution of 6 molecules of oxygen, only 12 NADPH formed and 16 ATPs formed. 12 NADPH formed, 16 ATPs formed. But truly, for the formation of one glucose or one fructose you take, we need 18 ATPs, 12 NADPH plus H plus. We need 18 ATPs, but here only 16 ATPs only generated during the evolution of 6 molecules of oxygen. The remaining 2 ATPs are provided by cyclic photophosphorylation. Through the non-cyclic photophosphorylation, 16 ATPs are provided. Through the non-cyclic photophosphorylation, 16 ATPs. Through the cyclic photophosphorylation, 2 ATPs. Okay, each NADPH is equal to 3 ATPs. So we have 12 NADPH, 12 into 3 ATPs, that equal to 36 ATPs, and directly 18 ATPs. So totally we need 54 ATPs to produce a glucose molecule. Of that asymmetry power, 18 ATPs directly utilized, and remaining 36 ATPs are utilized in the form of NADPH. So like this, quantum requirement is a light quanta that are required for the evolution of one oxygen. So if 6 oxygens are evolved, that means one glucose is